Okay, so this is the second part of the homework review for homework number 5. This is an innocuous little proof, innocuous seeming little proof. If S then T yields T or not S. So if S then T, assumption, and we want to show T or not S. Now here, of course, we're being asked to prove a disjunction, not prove something from a disjunction. So our strategy is going to have to be a little different. Usually when we approach proving a disjunction, we think in terms of proving one of the disjuncts and then just adding the other one in by disjunction introduction. But we've only got one assumption to work with, if S then T, and it's not at all clear what to do. There's no rule that we have that we can use to operate on if S then T with. Now, one of the things that people who are just starting out here will do when they can't think of anything else to do is they'll see the conditional and say, well, how about hypothesizing S, right? Hypothesizing S. And they're doing that just because they can't think of anything else to do. But that's pointless, and it's important to have a really robust understanding of why. The only reason for hypothesizing S in a case like this would be to derive T. And then you would just end up proving if S then T, which you already have in your assumption. So here's a very important mantra. Never prove your assumptions. Okay, that's just pointless. Your assumptions are given, so when you're doing that, you're just involved in a really absurd activity. So now really it's not clear that you have anything you can do, okay, except to proceed with negation introduction. And there's 3 conceivable ways you might approach this. You might approach it by hypothesizing not T, and then hoping to derive a contradiction from that. And if you did, then you'd have T, and then you could just add in not S. Or you could hypothesize S and hope to derive a contradiction from that, and then just use disjunction introduction to add in T. Both of those are worth thinking about, but when you do think about them, you'll realize that not T is in no way going to contradict if S then T, and S is in no way going to contradict if S then T. So after playing around with that, you're just going to realize that that doesn't work. So the only other option here is, and it's really not clear unless you have a lot of insight. Let's get rid of this bogus approach, is to just hypothesize it's not the case that T or not S. Now I emphasize that this is for negation introduction. This is kind of a last-ditch effort after you've thought about everything else. Because when you do this, it's still not at all clear that there is a way to generate a contradiction. So this proof is one that we would classify as really requiring a little bit of creativity. The other ones, you really just have to understand the rules. But this one requires some playfulness, requires actually being interested in messing around with stuff until something works. Now, when I help you with it, it's very hard to reproduce that messing around aspect without it just becoming interminably long and irritating. So I'm not going to do that, but you should. So the way to approach this is to say, well, and this is completely new for us, is to try to imagine what it is that you would like to contradict. So in the previous problems, we were just saying, well, let's just do some stuff and probably a contradiction is going to pop out. But now we actually have to kind of strategize toward a particular contradiction. So let's ask ourselves if there is any way that we can actually contradict one of these formulas. And what I'm going to ask is if there's any way that I could contradict the hypothesis itself. Okay, so suppose I hypothesized, and notice, and this is the first time this is happening, again for negation introduction. Suppose I were to hypothesize not S. Okay, suppose I were to hypothesize not S. Now, I totally understand what you'd be saying. Well, why? Well, look, because if we hypothesize not S, okay, then we could do disjunction introduction and get T or not S. Now that feels like some sort of progress, right? Because that actually does contradict. It's not the case that T or not S. So let's just go with that. That would just be by 3 and disjunction introduction. And now, because we have created a contradiction, we are going to be able to say T or not S and not T or not S. There's your contradiction, right? 2, 3, conjunction introduction, right? That gives us a contradiction, and that allows us to write not S by 3 through 5 negation introduction. And that gives us S by 6 and negation elimination. Right? Well, that's cool. Is that progress? Well, actually it is, or it seems to be, right? Because now where are we? Well, we're back to needing a contradiction, right? We discharged our second hypothesis, but we're still now trying to contradict something for our first hypothesis. But now look what we can do. We can take S, right? Feed it into 1, and we're going to get T. And if we get T, then we can create T or not S, which is going to contradict 2. Okay? And that's the key. So T by 1, 7, conditional elimination, and then T or not S by 8 and disjunction introduction. And now we have a contradiction between 2 and 9. So T or not S, and not the case that T or not S by 2, 9 conjunction introduction. And there's your contradiction. So notice how important it is in both of these contradictions to be able to recognize a contradiction between formulas that are not atomic formulas, right? If you couldn't do this, you wouldn't be able to actually do this proof. And so now we get to say not, right? Negating the hypothesis, not T or not S. Drop a big long line. Two through 10, negation, introduction, and then finish it off with another negation, elimination, right? So 11, negation, elimination. So that is a really cool, fun proof. Of course, very frustrating until you figure it out. If you followed these steps, that's great, but as I've said already, that doesn't mean you understand it. What you need to do is shut it down and see if you can do it on your own, then come back. All right, for this next one, I haven't written out the full sequence because I didn't feel like it, but from these three assumptions, S and R, if S or M, then Q, and if R or L, then not Q, we're expected to derive simply P, which I've written over here on the right. Okay, so this one is kind of funny, but basically if you look at these three assumptions, think about the rules at your disposal, you'll see that they imply a contradiction on their own, right? S will give you S or M, which will give you Q. R will give you R or L, which will give you not Q. So these assumptions are jointly contradictory. If you just took these assumptions and did a truth tree on them, every branch would close, even without adding in P. They'd close also if you did add in P. They'd close if you added in anything because they're jointly sufficient to produce that contradiction. So that makes this proof pretty straightforward. It's just a little odd because P is not going to generate your contradiction. You are going to have to hypothesize not P, but that's just sort of a pro forma aspect of the proof because the contradiction is available before you do that. So there's different orders in which you could do this, but the obvious thing to do here is S by 1 and elimination, S or M by 4 and disjunction introduction, R by 1 and elimination, R or L by 6 and or introduction, and you've got Q by 2, 5, conditional elimination. You got not Q by 3, 7, conditional elimination, right? And then you say, oh, there's a contradiction there, that's fine, but don't put it together yet. Now just go ahead and hypothesize for negation introduction, not P, right? You know how to take it from here. Then you've got Q and not Q. This is the weird part because not P didn't generate Q and not Q, but that doesn't matter. That's not a formal requirement. So 8, 9, conjunction, introduction. And then that gives you not p by 10 through 11, negation introduction, which gives you p by 12 and negation elimination. All right, this next one takes us to kind of another level of maybe not difficulty, but tediousness. And the reason is that the assumption is a disjunction, but one of the disjuncts is also a disjunction. And that means that we're going to be involved in a couple of OR eliminations, one inside of another. So you still want to stick to your basic approach, and that means you want to hypothesize not S, because the conclusion is a conditional. So hypothesis for conditional introduction. And then when you see what you're trying to prove, the consequent is also a conditional. You want to hypothesize the antecedent of that conditional as well for hypothetical, for conditional introduction too. So now all you have to do is derive n, but you have to do it from a disjunction on line 1. And so what you need to show, right, is if m or n, then n, and then you need to show if s, then n. So let's first show if m or n, then n. So to do that, we will hypothesize, again for conditional introduction, m or n. So as I said, you've now got a disjunction from which to prove n, and so that's going to involve you in another disjunctional elimination, okay? So in order to do this project, you first must, this project, show if m, then n, and show if n, then n. Okay, so yet another hypothesis for conditional introduction. Now it's m, and from this you want to derive n, and you'll notice this is going to be pretty easy because you've got both m and not m. So what you're now going to do is hypothesize negation introduction. Yes, no kidding. 1, 2, 3, 4, 5 hypotheses in a row. So now you've got not n, and now you can simply write m and not m by 3, 5 conjunction introduction, which gives you that it's not the case that not n. So 6 through 7 negation introduction got rid of that hypothesis. And of course, now we need n, and that's by 8 and negation elimination. So now we can assert if m, then n, which means we've done this. So now we need to show if n, then n. Well, that's super duper easy. We just hypothesize n, and having hypothesized n, we in fact have n, so that's just if n, then n, and weirdly 11 through 11 conditional introduction. Okay, so we've shown if m, then n, and we've shown if n, then n, and so now we get to assert n, and that's by 4, our disjunction M or N, 10 and 12, and that's disjunction elimination. And having done all that, we have now shown if M or N, then N. Drop a line, and that's 4 through 13 conditional introduction. Okay, so we've done the first one, and now we just have to show if S then N. So hypothesize S for conditional introduction, and you'll notice you have not S at the very top, so the same kind of thinking. We're just going to hypothesize not N, hypothesis for negation introduction, which gives us S and not S. Now, of course, I know it's kind of weird to say which gives us, because S and not S did not result from hypothesizing not N. And this can be kind of confusing. We kind of expect the negation introduction hypothesis to somehow cause the contradiction, but that's not a requirement, and very often that's not what happens. Very often there's just some pre-existing contradiction, and the negation introduction is just to comply with the formalism. So here we have 2:16 conjunction introduction. That's going to give us not N by 16 through 17 negation introduction, which gives us N by 18 and negation elimination, which gives us if S then N by 15 through 19 conditional introduction, and that's the other conditional we wanted. So now we get to assert free and clear N, and that's by the original disjunction 1 and 14 and 20. Disjunction elimination. Okay, so we got N, and we've discharged every single hypothesis except the first two conditional introduction hypotheses. So to finish this up, we'll have if not M then N, three through 21. Conditional introduction, and finally our conclusion, if not S, then if not M, then N. So 2 through 22 conditional introduction. Okay, so that's long and it's tedious, and it really requires a lot of attention to detail, but we are just using all of the concepts we've learned. There was nothing conceptually new in this. Okay, the next one tells us to derive from, it's not the case that if P then Q, P and not Q. And if you're in touch with what we've done recently, you'll recognize that here we're replicating the rule that we applied for negated conditional in the refutation tree system. Okay, this next one again looks like a simple little problem, but it turns out to require some creativity. So as usual, I encourage you strongly to grind on it and exercise some of that creativity before coming to the solution. And also, if you hear me say something that makes some, a light bulb go on, then just turn it off and see if you can finish the proof. That's a big deal too. Okay, so we're being asked to derive a conjunction, okay? And as I've said before, the usual way to prove a conjunction is to prove each conjunct independently and then just put them together at the end. So that's going to be the strategy you want to employ first. So let's just first ask if we could prove P, okay? It's not obvious how to do that. This is just a negated conditional. But suppose we just play around with it and we say, okay, well, how about if I hypothesize for negated introduction, not P? Well, that might not seem like it's going anywhere. But if you stare at it for a while and think hard enough, you might see that it is going somewhere. So ask yourself now what you'd be able to prove if you were to hypothesize for conditional introduction P. Or let me propose a different way of thinking about it. When you've hypothesized not P for negation introduction, you're looking for a contradiction, right? So then you say, well, what could I contradict? You look for something to actually contradict, okay? So you might ask yourself, is there any way for me to contradict the assumption? And that would mean, is there any way for me to prove if P then Q? So what if you were to hypothesize P, right? Well, that gives you a contradiction. So you can derive Q, right? Hypothesize for negation introduction, not Q. P and not P. You see how it's working? By 2, 3, conjunction introduction. And that gives you your not Q. So 4 through 5, negation introduction, and that gives you Q. By 6, and negation elimination, and that gives you if P then Q. By 3 through 7, conditional introduction. Okay, so you just contradicted your assumption, which is great because now you can assert not the hypothesis, I am jumping the gun, right? So what can you assert? You can assert this contradiction, if P then Q, and it's not the case that if P then Q, right? 1-8, conjunction introduction, and this allows you to assert not P all the way back, right? So 2 through 9, negation introduction, and 11 gives you P by 10 and negation elimination. Whew. So where are we now? Well, we've got P. We got the first part, right? So now we have to try to get not Q. But that was productive, and presumably this strategy will work again. So go ahead and try that one on your own before just watching me. So what I'm going to do is I'm going to hypothesize Q, right? I could do not q, but that's just going to involve one extra step. So I hypothesize the equivalent of not q, which is q. Hypothesis for negation introduction. And once again, I ask myself, is there any way for me to contradict the assumption, which in this case would be, is there any way for me to produce if P then Q? Same question, right? So what am I going to do? Again, I'm going to hypothesize P, right, for conditional introduction. And now I want Q, but Q is right there on line 12. Now I can't just rewrite Q. Someday when we're grown up, we'll be able to do that. But now we need to just create an expedient that allows us to do that. So we just need to do conjunction introduction followed by conjunction elimination. You can conjoin Q with anything available, including Q itself. So if I want to be cute, I'll write Q and Q by 12, 12, conjunction introduction, and then I'll get Q by 14 and conjunction elimination. So now I have if P then Q. (13 through 15), conditional introduction, and once again I've created the contradiction. So if P then Q, and it's not the case that if P then Q, by 1 and 16, conjunction introduction, right? And now that allows me to assert what? Not Q, right? So not Q, negation of the hypothesis, 12 through 17, negation introduction. And now I'm done, except for the last step, which is just P and not Q by conjunction introduction on lines 11 and 18. Okay, so some of these simple looking ones turn out to be long and require some insight and creativity. Those of you who are enjoying this will find them the most satisfying to do because it's not just mechanical feeling, kind of the same kind of insight you get when you're solving interesting mathematical problems. But I know and appreciate that not everybody finds this fun. S if and only if T, T or S, and from this we're supposed to derive it's not the case that if T then not S. So stick with the procedure, right? You notice that you have a disjunction, so you're going to want to almost certainly use disjunction elimination. So independently you're going to want to show, right, what? If T, then it's not the case that if T then not S, and if S, then it's not the case that if T then not S. All right, so let's try the first one. Hypothesize for conditional introduction T, right? Trying to build the first conditional. And you can see a pretty direct route here, right? So we're trying to show that it's not the case that if T then not S. So let's go ahead and hypothesize that it is the case that if T then not S for negation introduction. And let's go on a hunt for a contradiction. Well, not S by 3, 4, conditional elimination. And that's going to lead to a contradiction, right? Because we can get if t then s by 1 and by conditional elimination, and that gives us s by 3, 6 conditional elimination, which gives us s and not s by 5, 7 conjunction introduction, right? And so that allows us to assert the negation of the hypothesis, which in this case is if t then not s, right? So 4 through 8, negation introduction, and there we have our first leg of our journey. If t, then it's not the case that if t, then not s. Drop a line, and 3 through 9, conditional introduction. Okay, so if you followed that, you should be able to do the rest of this on your own. So do it, come back and check and see if you did it right. Hypothesize S, right? All right, so this is a little bit different situation, isn't it? Because we hypothesize S, which makes sense because we're trying to demonstrate this conditional. If S, then if not, if S, then it's not the case. If T, then not S. And it makes sense to proceed as we did above again by hypothesizing the negation of the consequent, which in this case again is if T, then not S. But before, things were nice because on lines 3 and 4 we were just able to generate not S. But you can't feed S into if T, then not S. So it's not immediately obvious where our contradiction is going to come from, is it? I mean, if you're feeling lonely and scared, you might say, well, I mean, it's like 13 if T, then S by 1 and by conditional elimination. Isn't that a contradiction between 12 and 13? And the answer, you know in your heart, is no. Contradiction is just a formula and its negation, and this is not a contradiction because it's not a formula and its negation. So if you grind on this a little bit, you might recognize by just staring at 11 and 12 that together they have to imply what? They have to imply that it's not the case that T, right? Because if T were the case, you'd be able to generate not S through conditional elimination, and that would be a contradiction. So 11 and 12 imply not T. Let's go ahead and make that clear by hypothesizing for negation introduction T, right? Getting not S as a result, so 12, 13, conditional elimination, which allows you to write S and not S by 11 and 13, conjunction introduction, from which we can infer not T, right? So 13 through 14. Oops, I made a mistake in numbering things. Let me renumber them here. All right, so not T by 13 through 15, negation introduction. And what good is that? Well, remember, we're still looking for a contradiction, but now, right, we have if S then T by 1 and biconditional elimination. And that does give us a contradiction because now we can generate T by 11, 17, conditional elimination. So now T and not T by 16 and 18, conjunction introduction, leads us to it's not the case that if T then not S. 12 through 19, right? 12 through 19, negation introduction. And so there's our second conditional, right? So now we have if S, then it's not the case that if T, then not S. A little tight. By 11 through 20, conditional introduction. Right, so there we go. Last step is just disjunction elimination. We get to assert free and clear. It's not the case that if T, then not S. By 2, 10, and 21. 2, 10, 21. Disjunction elimination. All right, this one, if Q then R yields not Q or R, is actually just a version of a previous one where the atomic propositions were S and T instead, and the disjunction was in the reverse order, which doesn't really make it any different. So I'm not going to do this one, but if you didn't recognize it as one that we had previously done, it'd be a really good idea for you to go ahead and do it again. Okay, in this last one, P or P yields, if not P, then Q, is just a good solid one to end up with, where we exercise the routine that we've learned. So if you wanted to think about this in semantic terms, whether it makes sense that this would be the case, well, P or P clearly implies P, right? So, and from P, we would know that if not P, then Q, because P and not P is a contradiction, which implies anything at all. So begin by hypothesizing not P, right? Or hypothesis for conditional introduction. Then you have a disjunction, and so what you need to do is show if P then Q, and you also need to show if P then Q. But of course, those are the same, so you don't need to show it twice. You only need to show it once, and then just cite the line twice in your or elimination justification. Be no harm in doing it twice, it's just not necessary. Okay? So we will hypothesize P. Now we want Q. And the only way we're going to get Q now is through contradiction. So we're going to hypothesize for negation introduction, not Q. Right? And that allows us to write P and not P by 2, 3, conjunction introduction. Hence, not Q by 4 through 5, negation introduction. hence Q by 6, and negation, elimination, hence if P then Q. By 3 through 7, conditional introduction. All right, you got P through P, if P then Q. If you've got it once, you've got it as many times as you like. So that means you have the original disjunction, you have if P then Q, you have if P then Q, and so now you can write what? Q, right? By 1, 8, and 8, disjunction, elimination. And finally, if not P, then Q, by 2 through 9, conditional elimination. Okay, and that is it.